Welcome to the Explainer. Today we're doing more than just solving a physics problem. We are going to learn a method, a system really, that can help you solve almost any challenge you're going to face in your studies. And we'll do it by tackling a classic problem together.
So, if you've ever looked at a problem like this one, with all its rods and wedges and angles, and felt that little knot of panic in your stomach, well, you are definitely not alone. This is problem 1.77 from a legendary textbook, Problems in General Physics by Irodov. It's a book famous for training physicists, and, let's be honest, for being incredibly challenging.
But here's the secret. This book isn't just a collection of impossibly hard problems. It's really a training ground. And, like any good training, it comes with a manual. Irodov actually gives us a guide to thinking like a physicist, and that's exactly what we're going to unpack.
Yeah, hidden in plain sight, right at the beginning of the book, Irodov gives us a toolkit. It's this systematic approach to deconstruct any problem, no matter how complicated it looks on the surface. And this process, this is what we're going to master today. At first glance, these steps seem almost, deceptively simple, right? There's no magic formula here. The real power of this method is in applying each step rigorously. And that's exactly what we're about to do with problem 1.77.
All right, let's get into the problem and see how this method builds our solution, one logical piece at a time. We're going to turn that intimidating diagram into a clear, straightforward path.
Okay, step one, understand the setup. What are we actually looking at? We've got rod A, and it's propped up against a vertical wall. It's resting on wedge B, which itself is on a horizontal floor. The goal? Find their accelerations. And we're given two huge clues. The mass ratio is n, and maybe most importantly, friction is negligible. That means all the surfaces are perfectly smooth, which, trust me, simplifies things immensely.
Now for a really critical step, we draw a free body diagram for each object. This just means we isolate it and draw every single force that's acting on it. So for rod A, we have three forces. First, its weight, mg, pulling straight down. Easy enough. Second, the normal force from the wall, pushing it to the right. And third, the normal force from the wedge, pushing up and to the left, perpendicular to the surface of that wedge.
And we do the exact same thing for wedge B. It's got its own weight, mg, pulling down. The floor pushes up on it with a normal force. And here is the crucial link. The rod pushes down and to the right on the wedge. Now, thanks to Newton's third law, we know this force is equal in magnitude and exactly opposite in direction to the force the wedge put on the rod. They're a pair. Okay, before we rush off to write F equals ma, there is a vital, intermediate step in our method, identifying the constraints. Think of constraints as the rules of the game that are imposed by the physical setup. They tell us how the objects can't move, which in turn tells us a lot about how they can move.
So let's list them out for this problem. The wall constrains rod A so it can only move vertically. The floor constrains wedge B so it can only move horizontally. This is huge. It means we already know the direction of acceleration for both objects. And the most important constraint of all, they have to stay in contact. This is the rule that ties their two separate motions into one single solvable system. All right, with our forces identified and our constraints listed, we've basically done all the physical thinking. We have everything we need to start building the mathematical path that leads to the final answer.
This slide here illustrates our goal perfectly. On the left, you've got all the known quantities, everything the problem gives you. On the right, that's what we're looking for, the accelerations. The game now is to use our physics principles to build equations that connect the left column to the right column. This right here is where so many students get stuck. You can see it, right? Intuitively, if the wedge moves, the rod has to move. But how do you write that down as an actual equation? This is often the key conceptual leap you have to make in problems with multiple bodies. The answer comes directly from our third constraint. They stay in contact. So just imagine the wedge moves a tiny bit to the right. Let's call it dx. The rod has to slide down the wedge's slope, dropping by a distance dy. If you look at the triangle formed by the wedge, you can see that the ratio dy over dx is just the tangent of the angle alpha. And if this happens over time, that same geometric relationship holds for their accelerations. So the rod's vertical acceleration, AA, has to equal the wedge's horizontal acceleration, AB, times the tangent of alpha. That's it. That's our kinematic link.
And now we get to apply Newton's second law. Let's start with rod A. We know it only accelerates vertically. So in the vertical direction, we have its weight, mg, pulling it down, minus the vertical part of the normal force from the wedge, which is n times cosine alpha. And all of that equals m times AA.
Now for wedge B. It only accelerates horizontally, so we sum the horizontal forces. The horizontal piece of the normal force from the rod, n sine alpha, is what causes the acceleration, so that equals m times AB. And there we have it. We have a system, 2 force equations, and our 1 kinematic equation that relates the accelerations. From here, it's just a matter of doing some careful algebra to solve for AA and AB.
So, what's the big takeaway? The crucial point is that this structured method, understanding the setup, identifying forces and constraints, and then building the equations, it isn't just for this one problem. This is the method. I mean, just look at the table of contents from Irodov. It doesn't matter if you're dealing with mechanics, thermodynamics, or even electrodynamics. This fundamental process of breaking a problem down into its essential parts, it stays exactly the same. The forces might change, the laws might be different, but the thinking process, that's universal. This toolkit basically trains your brain to see the structure inside the chaos. It transforms a really intimidating problem into a checklist, just a series of logical, manageable steps. It's about building a framework for how you think, not just memorizing a bunch of formulas.
You see, we've deconstructed problem 1.77 not just to get an answer, but to reveal a process. And by mastering this process, you really equipped yourself to face any challenge that comes your way in any chapter of this book and honestly, way beyond it. So, the real question is, what will you solve next?